Okay, good morning friends. So, today our topic is recursive robotic acceleration, we call it the inertia force here. So, I calculate the inertia force required to move this last link. Okay. Now, in case I apply or I move this last link using a motor here. So, I can calculate how much the torque will be required here. So, I calculate that torque. Then after knowing this is the torque required for movement of this body here, so I go back to the previous body, calculate how much will be the total inertia forces required, and then I can calculate the what will be the torque required the previous joint. So and so forth, I come to the first joint. So these are nothing but the dynamic equation which you might have learned already in Newton-Euler recursive algorithm, the same techniques. So this is the meaning of recursive, knowing information of one, finding out the information of the other. Please remember, recursion is different than the iterations. Okay. So now question is why recursive? Now I have here at least two logics here. One, because it is efficient, and efficient means what? Efficient means it requires less number of computations. If you count how many multiplications, additions, etc., required, one can count that thing, and recursive algorithm will require less, and obviously the reflection will be the less CPU time. Now, when you talk about recursive algorithm, in dynamics of robotics, we talk about two kinds of problems mainly. One is the inverse dynamics, where knowing the motion of the bodies, motion means position, velocities and acceleration, I calculate the torques required here. This is the inverse problem. So, here I have a comparison which is taken from a thesis, PhD thesis. Now, one of the recursive algorithm is the one which is shown in a solid line here, and you can see as the number of links are increasing, the benefits are also increasing. So, for industrial robots there is 6. So, still it is the less computations required. Then if I go to the problem of forward dynamics, where knowing the torque values of the joints, you want to calculate how the motions of the robot will happen. So, then there is a plot here, again the solid line is one of the recursive algorithms. Actually, all straight lines are recursive algorithms, except this one which is a cubic order here, this is not a recursive one. So, here also as you see, the number of links increasing, the benefits are also increasing, but even for 6 it is somewhat beneficial. So, the reference is the PhD thesis here, and which is actually a book now, Dynamics of Tree Type Robotic System. So, one is the computational time is less, that means it is more efficient. Another reason the recursive algorithm should be used, they are numerically stable. What is the meaning of numerical stability? Here I have an example. Suppose in recursive forward dynamics, that means knowing the forces, the joint torques, if you want to calculate the motions, means joint acceleration is the first thing to be computed here. So, if you use a recursive algorithm, the time versus joint acceleration plot looks somewhat like this on the left hand side, whereas in the right hand side you can see there are a lot of spikes are coming. Okay. Now, to know the motion, we have to integrate them. That means, from the acceleration we have to get the velocity and the position, which you can finally see in an animated form maybe. So, here if you whatever numerical integration schemes you are using, this is relatively smoother than the right hand side. So, the integration results will be relatively better here. So, which means you will get a more realistic feel. Otherwise, what may happen in a given system, it may not be unstable, but because of the algorithm you have chosen, it may show that something is widely changing. So, your interpretation may be said this is unstable, but actually it may not be. One such case I am showing it in my next slide. Suppose I have a 4-bar linkage, and I have done the analysis and I want to show its animations. In unstable algorithm if you use, you may see after some time the 4-bar linkage looks like the dotted lines here, where this link number 3 and 1 have separated out, which cannot happen actually, right. If you wanted to get a real 4-bar link, never it will happen. Okay. Either it will not move, it will stop, okay, but this separation will not happen. So, this separation is a cause of one of the numerical instability or the numerical problem. In this case, we call it a constraint violation. That means, the joint which is placed here to bind these two links have got separated out. So, after being convinced that why a recursive algorithm should be used, now let us go back to what are the formulations used for the robot dynamics. Now, these are two very classical one. One is the Euler-Lagrange formulation, where ddt of del L del q I dot minus del L del q I equal to tau I. Now, L here stands for the Lagrangian, which is equal to kinetic energy minus potential energy. Q I is a generalized coordinate. So, q I dot will be generalized speed, ddt is the time derivative, and tau I is the generalized force. If for our robotic systems, if generalized coordinates are the joint angles and tau I will be the joint torques. Now, the next one is the Newton-Euler equations. The first we write Newton's second law, mass into acceleration shown as V I dot is equal to the force. Okay. This we know from our high school. The next one is the Euler equations of rotations. No, I omega I dot, I stands for mass moment of inertia of the ith rigid body, and omega I dot is the angular accelerations, and in the right hand side n I is the moment. Please remember the second equation, the rotational equation, that I should be with respect to the mass center, or it has to be with respect to the fixed origin in order to have this expression satisfied. If you are choosing some other body, this expression has to be different, please remember that. Now, both has its advantage disadvantages. Now, for a rigid body Newton-Euler equation will lead to 6 equations, 6 scalar equations. The first 3 are for the linear equations of motion, and last 3 are the 3 rotational equations of motion, 6. So, if you have for our robot, suppose 6 bodies are there. So, 6 into 6 36 equations will be generated. So, even in order to find out the joint torque here, you will end up also calculating the reactions coming on the bodies which are like this body and that body, but all of them are not required. They are required to keep the links intact. What is required for us is the joint torque, but you have to calculate others. Now, for inverse dynamics they are not actually required, but we calculate it because of the formulations here. So, that is a disadvantage for us, whereas in case of Euler-Lagrange you require only the joint torque, you should be able to get it from this expression. That is an advantage, it is in a compact form, number of equations is less. However, you have these complex calculations to be done, partial derivatives, time derivatives, etc. Now, in one of the recursive formulation which I will present today is called a D-knock based recursive formulation. Here we try to get advantage of both the features. While Newton-Euler has some feature which is like easy to understand, because from our school level we are studying it, so we can understand it, and also it is based on the vectorial concepts, right. So, we can understand what is the position, how the velocity will be moving in certain direction, whereas in case of Euler-Lagrange it is somewhat little abstract, unless you understand better, it is little difficult. So, what we do is we start with Newton-Euler equations. Now, in this equation m I T I dot plus W I m I T I is equal to small w I. What I am doing is basically putting it in compact form. As I tell to my other students, now as if you have to travel from your hostel to your home, you do not take your clothes and books just like that thing. What you do, you put it in a box, right, and in a manner so that you can easily unpack it when you go back, and also it becomes a compact for the travelling purpose. So, here also I put these two equations in a box, and these are bigger matrices. M I has this definition that on the top. Now, I am just writing rotational equation first and then the linear equation. So, I into omega I dot, that is the way the multiplication will carry forward. You just sit down with your pen and pencil and paper, and you will be able to get this right. So, M I as you see it here contains I I, which is a 3 by 3 inertia tensor or the inertia matrix. This is a 0, contains all 0. So, it is a 3 by 3 0. This is M I is a scalar mass of the ith body, and this 1 indicates here is a 3 by 3 identity matrix here. And in the next term you have small omega I cross 1. Omega I is actually the angular velocity of the ith body, and cross 1 it is a symbol for the cross product matrix, which means omega, which means I will just show you on this paper. So, if I write omega I cross 1, if you have x a vector, then the definition is omega I cross x. So, since this operator produces this cross product, so we call it a cross product tensor or loosely cross product matrix. Okay. It is just a symbol. Some people use it this kind of symbol to define the same, but we prefer to use the following because it gives immediate understanding that okay, if you have x on the right hand side, it will give you the cross product. So, we come back omega small w I we call it a range. Now, it consists of this moment and the force, and this small t I is called the twist. So, this M I we call it mass matrix, capital W I we call it an angular velocity matrix because it has angular velocity inside. This is a twist, just like a twist motion which contains linear and the rotational, and the range like a range you apply to loosening a nut for example. So, we start from this okay, and then we do some manipulation, so that we come back to the Euler-Lagrange equation, which gives the minimum number of equations for the robotic system we have. So, block wise this is the thing what we want to do it. Now, how we convert from Newton-Euler to Euler-Lagrange. So, we do this trick, actually it has its proof which can be seen in the book. So, we write the link velocities, and when I say link velocities, not only for the ith link, all, that means 1 to n. For our 6 degrees of freedom robot, it will be 6 into 6, that means 36 by 1 will be the size of the link velocities. And in the right hand side, I have the joint rates, which are theta 1 dot, theta 2 dot, theta 3 dot. For 6 degree of freedom, it will be up to 6. So, right hand side is 6 by 1. So, in the left hand side, I have 36 by 1 for 6 degree of freedom robot, and in the right hand side, I have 6 by 1, and I correlate them with a matrix which is called the velocity transformation matrix. I will show you little later how they have to be computed. So, we call it a DNOC matrix because it is consisting of 2 block matrices, which I will show you again later. Then what we do, we pre-multiply all this Newton-Euler equation by the transpose of these DNOC matrices, and we get the minimum number of equations, which are nothing but the Euler-Lagrange equation. Okay. So, these operations will be done in a manner because of the structures of NL and ND, which are the DNOC matrices, we can show that they can be computed recursively, which I will show you little later. So, what are the advantages of such formulations? Now, analytical expressions of the vectors and matrices which are showing up in the equations of motion, you can get the analytical expression, which means you do not use the computer at this stage. So, you can get the expressions, and the expressions are always useful for us because it provides the physical interpretations, right. We know that what mass values are actually causing a large number of the say inertia elements. Then the decomposition of the inertia matrix, we require decomposition of the inertia matrix at some stage when you do the forward dynamic, that can be done even analytically or symbolically if required. And some other advantages, like you can looking at the expressions, you can look that how the model can be simplified. So, now I wanted to bring the concept of DNOC through this simple example. Let us see, I have a moving mass, a mass moving in a straight line, okay, and this motion is caused due to the force applied on it, which is F. Now, F has two components, one is the horizontal component F, small f, and then this vertical component F v. Now, we all know for such system, now the motion will be caused by this small f, whereas F b will not create any motion, but it will create actually the reactions, which means the table will be supporting not this mass to fall. So, the vertical component which will actually create reactions and the horizontal. So, the best preferred direction of this force would be that F vector would be put at the horizontal level. So, all the force will get converted to motions. So, since we are interested in how much force to be applied to this thing, I am more interested with this small f, no, not this F v. So, my formulation starts like this thing, as I told you that first we will write the Newton-Euler equation. In this case there is no rotation because mass is assumed as a point mass. So, it will have a linear equation. So, I draw the free body diagram, means I remove the table from here, but replace the table with a constraint force here F c. Mass center is indicated with this vector small c boldface, which means I draw the free body diagram and then I write the Newton's second law. The external forces applied on it, which are here, maybe the force applied by me, the constraint forces, that reaction forces, coming from this table, is equal to the mass into the acceleration. Okay. Now, actually this body is not free, this body is actually sitting on the table and that too moving in a straight line. So, if I indicate this direction with the unit vector small I, so then I can write my constraint. Constraint means velocity can happen only along the x directions. So, that velocity I am writing x dot, the magnitude, and the unit vector directions, that is the x directions. So, c dot is equal to x dot I. Now, what I told you earlier that the matrix, in this case this is a vector quantity only, this is my NOC. Now, NOC stands for natural orthogonal complement. The orthogonal complement is a term used in linear algebra, and this word natural we use it because we get these expressions from the velocity expressions written in a natural way, we do it in mechanics. So, this I, and if you go back to my previous one of the previous slide, that transpose of this matrix, if you multiply you get the minimum order. Let us see. So, this is now my I. Now, I multiply this Newton's equations with the transpose of it, both sides, then what do we get? See, I transpose I will be a unity, right. So, I transpose I will be f, which is this f here, okay. And let us see, I use the pointer here, okay. So, this will be this f, then I transpose j will be what? I and j are orthogonal to each other, right. So, it will be 0. Okay. So, that is why these components are not showing up at all. So, this f b and f c has a j as a coefficient. So, I transpose j is 0, it is not there, and in the right hand side I have I transpose I, which is again unity. So, I end up with the same equation, okay, which is the Newton's equation for unidirectional. If you use Lagrange formulation, it will be the equation. So, I started from the free body expressions, imposed the constraints and end up with the minimum set of equation, because this system has 1 degree of freedom and I get one equation of motion, which is the force is equal to mass into acceleration along the direction. Okay. So, the concept of NOC is exactly this one. So, whichever component are not contributing to the motion, can I vanish from my equation of motion, because this property exists I transpose j. So, in other words, all the free body diagram and the equation of motions I get, in case of geometrical thinking, you actually project on the direction of motion. So, to take a simpler example, if this mouse is for example, moving on this table. Okay. So, if I have a force applied in any general direction, so I find out that matrix NOC and then multiply means actually I am looking for this horizontal component of the forces which will actually create the motion. Okay. So, if you understood that concept, okay, rest of the things are basically routine arrangement of equations of motions and the computation in a little systematic manner. Okay. So, again I go back to the free body equations of motion for ith body which I told you earlier. First one the 3 scalar equations for rotations and the last 3 are the 3 scalar equations for translation. I put them in a box, that means I arrange them in a bigger matrices, and this mass, twist, angular velocity matrix and the range which I have already showed you earlier. Now, I wanted to combine for all bodies. So, here what I am doing, I am separating all the bodies, I am imagining bodies are separated out, and now if you put them together this m I. So, which means what? I first write this equation for the first body, I write this equation for the second body, and if there are n bodies are there, I write them in a separate form, and then I put them together and I get these 6 n equations of motions. How? Let us see here again. So, I have m 1 t 1 dot plus w 1 m 1 t 1 is equal to small w 1. So, the vectors I am indicating with arrows, m 2 t 2 dot plus w 2 m 2 t 2 is equal to small w. Suppose if I have two link system and if I have to put them together, I will write it m 1 big 0 m 2, right. So, t 1 dot t 2 dot. Now, it is like small pencils and erasers we put in a small case, and then when you go home we put it in our suitcase. So, something like that. Okay. And similarly, you can arrange this one also. Now, this will give you capital W, this will be capital M, the capital T is equal to small w. So, now if each of them has 6 and now I am doing it for 2 bodies. So, this size will be 12 by 12, okay, and similarly for the other. So, that is the same thing. So, it is a block diagonal here, right. So, on my slide this is the one I am showing, this capital M nothing but the block diagonal of m 1 m 2 up to m n. Okay. So, so far I have written all these bodies separate, but actually for this robot they are not separate, they are coupled with a revolute joint. So, if a body is connected, if the ith body is connected with the jth body by a revolute joint, how can I write its velocities? That will lead to the velocity constraints. So, that is my next slide. The kinematic constraints are actually in this case are the velocity constraints. So, knowing the velocity of the j, that means angular velocity of the jth body, okay, and I add the angular motions coming from the revolute joint, I can calculate the angular velocity of the ith body. Similarly, from our mechanics, if I want to write the velocity, the linear velocity of the ith body, in this case this body here, knowing the velocity of the jth body, and in this case we are considering the velocity of the mass center, then we can write velocity of the jth body which is here. From there I come here, the velocity of this point here which will be this velocity, that means velocity of C j plus omega j, that means angular velocity of the jth body cross r j. So, this is the one I have written omega j cross r j. Then since omega I has a different velocity, so now it is omega I cross d I. Okay. So, knowing the velocity of one body, I go to the velocity of the next body. Again my intention is to do everything in a systematic manner, just like before going home I put in a box. So, here I want to put it in a box. So, now left hand side I define as a twist. So, T I, and then I introduce a matrix called B, B I j into T j plus P I theta I dot. Now, P I B I j has this expression and P I has this expression. Now, this expression you can look into it later on, but let us look into its physical interpretation. What is B I j means? I have a definition here. Bij means is a twist propagation. By the way, twist you can remember is a generalized velocities in a sense that it has angular velocities and the linear velocities put together, that is twist. Now, what is the meaning of twist propagation matrix here? Suppose this theta I is my joint motion here, which is the revolute joint. Now, if you block it actually, if you say you welded this portion, okay, then what happens? Theta I